Welcome to the course on TensorFlow. In this video series, we're going to look at TensorFlow-Slim. TensorFlow-Slim is a very nice wrapper that allows you to build and train more complex and deeper TensorFlow models in a much easier and intuitive way. This course is an intermediate to advanced TensorFlow course and assumes that you have some kind of experience working with TensorFlow and have some basic knowledge in machine learning. This course is for TensorFlow users who want to build and train more complex deep learning models and don't want to deal with the headache of growing code complexity as those models get deeper and deeper. This course introduces TensorFlow-Slim. It is a library in TensorFlow that makes building, training, and evaluating complex deep learning architectures much easier. It makes it more maintainable and readable. Yet at the same time, it is still a very flexible framework that is fully compatible with native TensorFlow, allowing you to fully customize your algorithm in whichever way you want, while being able to abstract the complexity of some part of the model and make it easier to read and easier to digest. So in this course, we're going to be spending lots of time building a number of models, and then we're going to have fun training them, evaluating them, and playing around with the architectures. Therefore, this course has a number of prerequisites that are by no means mandatory, but will definitely help you understand the material in the future lessons. So let's go through some of them. So it would be useful to have some basic understanding of data science theory. For example, what is train and test split? And why do we do that? What is the difference between overfitting and underfitting when you're training a model? Having some kind of intuition about what is the bias variance trade-off. Having some kind of understanding about what we mean when we talk about feature space dimensionality of our dataset, and how does that compare to our model complexity. It also would be useful to have some understanding of deep learning theory. For example, backpropagation is a very important concept in deep learning, and this allows us to backpropagate the error signal throughout our model. It's also important to understand that neural networks are essentially large amount of parameters and weights, represented in tensors or even sometimes simply matrices. And it's also easier to visualize neural networks as building blocks, as layers that you can stack together and configure in different ways. Every neural network is trying to optimize an objective function and has a loss function that is related to the task it's trying to solve. Is it a regression task or is it a classification task? And training is accomplished through optimization. And in the case of deep learning, it is often accomplished through stochastic gradient descent, where you're feeding batches of data into the model in an iterative manner. This course also assumes a little bit of knowledge about the basics of the TensorFlow API, being able to initialize variables, being able to build a graph and start a session, and from that session, train and evaluate your model. The course objectives for this TensorFlow-Slim video series are the following. By the end of this course, you will be able to build readable and maintainable deep learning architectures with the Slim API. You will be able to define complex models in a much more compact way by eliminating the boilerplate code that plagues many of the deep learning algorithms at the moment. You will have build and train feedforward network, an image classification model, and a text classification model. You will have experience iterating and experimenting in a rapid way with different high-level layers, loss functions, optimizers, regularizers provided by the Slim API. You will be able to implement fast and efficient routines for model training, model evaluation, and hyperparameter tuning. You will also learn to fine-tune pre-trained models, as well as using transfer learning to take models that were trained on a different task and use it for another task. In this lesson, we are going to learn how to manipulate and create variables easily using TensorFlow-Slim. But before we dive in, let me first go over a couple of concepts, just as a review and to give you some context on what's coming up. When you create a neural network or machine learning model in TensorFlow, what you're creating in fact is a computational graph. A computational graph is a directed graph where nodes are connected by directed edges. Here we have an example of a graph on the right. The nodes represents the mathematical operation of that graph. These are the computations that define your model. The circular nodes here are the operation of this graph. Those can be matrix multiplications, adding a bias, computing the softmax, computing the cross entropy, and so on. The edges represents the multidimensional data arrays that we refer as tensors flowing between the nodes. They represent how the output of an operation connects to the input of another operation. Let's also review variables in TensorFlow. In TensorFlow, variables are mutable nodes in the computational graph. They are tensors of data which have a shape, an initial value, and a name. In the graph on the right, the tensors are represented by rectangular dotted lines. Here we can see in this layer that the weight and the bias is used as input into the operations of the graph. Since those variables are mutable, their value can be updated. And we can see here in this section of the graph how each variable is being updated at every training step. In TensorFlow, variables are often used for holding trainable parameters in the deep learning model. These can be saved to disk and reloaded later for either further training or for inference, for example, during prediction. However, there exist other types of variables in TensorFlow. You have the regular variables that are not necessarily representing the model, but are used for learning and evaluation, but are not required for performing inference. Then you have the classical model variables. These are the trainable variables that represents the model itself. These variables can be updated during training and loaded from checkpoints and are used in evaluation and inference. You also have the local variables. These variables are transient variables that only exist for the duration of the sessions and therefore are not saved to disk. Finally, you've got the global variables. These variables persist across every training iteration and are globally accessible. So what is TensorFlow-Slim providing us for variables? It's giving us a set of thin wrapper function that makes it easier to create and manipulate variables in a more consistent way. In this notebook, we're going to cover the following Slim functions. If you're interested in learning more about all the provided variable Slim functions, check out this file right here. Now, let's dive into the code. So let's first import TensorFlow and import TensorFlow-Slim. Then we can also import some helper functions that I've provided for you. This function will help you inspect the variables and inspect the layers. The specific implementations of those functions can be found in the utils folder. We're going to first define and create variables with native TensorFlow, and then we're going to repeat the same thing, but this time with TensorFlow-Slim and see how that differs. First, we need to initialize a graph. Then within that graph, we're going to start initializing different variables. So for example, we can start with a global variable. A global variable is accessible throughout the neural net, and for example, could be a counter that keeps track of the different iterations during the training process. This variable is a constant and will be initialized to 1. And since it's a scalar, it has a shape dimension of 0. The variable type is of integer, and we set it to trainable to false because this variable is not part of the model and therefore is not trained during the training process. We're going to give it a name of global step, and then we're going to tell TensorFlow that this is a global variable in the collection. Next, we're going to define a variable scope, and within that variable scope, we'll define other variables. We're going to call this scope TF native, and within that scope, we're going to pin a certain device. In this case, we're going to pin the CPU. Now let's initialize a model variable. A model variable could be, for example, the weights in the neural network. And therefore, the weights are trainable variables. And so we need to make sure that trainable is set to true. We're going to give it a name, weights, and we'll give it an initial value. In this case, the initial value is a truncated normal. This truncated normal is actually a tensor, a 4-dimensional tensor. So for example, this weight could be a weight in a convolutional neural network. And therefore, the first two dimensions represents the size of the kernel. So this would be a kernel of 3 by 3. The third dimension is the input feature space of the layer. And the fourth dimension is the output feature space of that layer. This weight represents the transformations within a convolutional layer. We can set the standard deviation to be 0.1 and then the type of the variable to be float. Lastly, we need to tell TensorFlow from which collection this variable is. And so, as we said, this is a model variable. We can define other model variables, such as biases. A bias is a constant that will be initialized to 0, but this time it's a vector. And we're going to give it a size 128 to match the previous weights. Similarly, the type is float. It's a trainable variable, and it's part of the collection model variables. If you wish to add regularization to your model, you have to add it manually by computing the L2 loss on your weights, computing the L2 loss on your biases, and then adding them together. It's possible to create other trainable variables that are not necessarily part of your model. To do that, you can set to training to true. In this case, we're going to give it a constant initialized to 0 with a shape of 2 dimensions. So this would be a matrix. For example, if we assume that this is the prediction matrix, then we could have a batch of size 32 and classifying over 10 classes. Therefore, that's why you have 10 columns. And then you can set the collection to be trainable variables, which is different from model variables. Lastly, we can initialize local variables, which are only accessible locally as opposed to global variables. So for this example, imagine we want to compute the accuracy. Then the accuracy is not a trainable variable because it's not part of the model. It is a constant and a scalar, so it has shape 0, but it's part of the local variable collection. Now we're going to use one of the helper functions provided to inspect and verify that our variables were properly initialized. So you can call the inspect variable function and pass in a list of all the variables we've defined earlier. What this function gives back is a printout of all the variable names and their shapes. So we can see that the first variable global step was initialized correctly with a shape dimension of 0. It's important to notice that all the other variables are prefixed with the name tfnative because those variables were initialized within the name scope tfnative. The weight matrix is, as expected, a 4-dimensional tensor. The bias variable is a vector. The prediction is a matrix. And finally, the accuracy is a scalar. Now we're going to define again all those variables, but this time with the TensorFlow-Slim API. TensorFlow-Slim provides us many wrapper functions that makes it easy to initialize and manipulate variables. I'm going to go over the definition of some of those wrapper functions, and then we're going to look at concrete examples. This is mainly for your own reference. So Slim provides us a function that is called get or create global step. This function will search through a graph for an existing global step. If it finds it, it will return it. If it doesn't, it will create a global step and return that new step. The Slim API also provides us with a function that is specifically designed for model variables. And this allows us to create and define model variables that are trainable but are only part of your model. Slim also provides a variable function that allows you to create and define trainable variables that are not necessarily part of the model itself. Slim also provides a function called local variables, and as the name suggests, it allows you to initialize local variables in your graph. Now we're going to recreate the variables from before, but this time with the TensorFlow-Slim. First, we need to initialize the graph. Now, to create the global variable, we simply need to call slim get or create global step. No need anymore to input the shape or the initializer. This function does it all for you and gives you back a scalar of type integer. This is exactly what you're looking for. Now you can also create a variable scope that we'll call TensorFlow-Slim weights. And within that scope, we're going to initialize our first model variable that we're going to call weights. We can see that now this API is very concise and brings all the parameters together. You can set the device within the function, even the regularizer. In this case, we're going to set the regularizer to be an L2 regularizer. You can set the initializer and the shape. To initialize the bias, it basically looks the same, but this time the initializer is a zero initializer and the shape is of a vector. Now if you want to initialize the trainable variable, you call the slim.variable function, and you simply need to input the shape of your variable and the initializer. In our case, it's again a zero initializer. Finally, to create a local variable, you call the local variable function and simply need to pass in the initial value and its name. Now we're going to inspect the variables that we've created with TensorFlow-Slim and check if they were defined correctly. For this, TensorFlow provides us with another great helper function to get those variables. This function is called slim get variable, and as opposed to before, where we had to list all the variables to inspect them, get variable will search through the graph for you and retrieve all the variables filtered by scope or variable type. Now, to inspect our variables, we need to pass in the output of the get variable function into the inspect variable helper function. For example, if we wish to get the variables that were initialized within a scope, we pass in the name of the scope, in our case, tfslim weights, and the function will return all the variables that were initialized within that scope. In our case, we had the weights and the biases. On the other hand, if we wish to inspect all the model variables, then we need to pass in into the collection parameter the model variable string. This will return all our model variables. In our case, it's the same thing. We've got the weights and the biases. And similarly, if we wish to inspect the trainable variable, we pass into the collection trainable variables. And here we'll get, as well as the weight and the biases, also the probabilities that we set as trainable when we initialize them. To get the global variable, Slim provides us with its own function called getGlobalStep, and that will return the global step variable. For the local variables, this is similar to the other ones where we pass into the collection parameter local variable. In our case, we just had the accuracy as our local variable. The getVariable function can be used for more than just the variables we initialize ourselves. It can also be used for collecting all the regularization losses. Here we can see that we've got an L2 regularizer for both the weight and the biases. Those regularizer variables were initialized automatically by the graph when we initialize those variables. In this lesson, we're going to learn about layers in TensorFlow-Slim. As you probably know, neural networks are made of layers. These are like building blocks that you can combine and stack on top of each other to create different models. TensorFlow-Slim provides you with a set of high-level layers that makes building models in TensorFlow simpler and more concise. Below, we've got an illustration of a 2D convolutional neural network. In this notebook, we're going to cover the following Slim functions. First, let's import TensorFlow. Then again, let's import our helper functions. First, we're going to look how we can combine convolutional layers and mask-splitting layers with native TensorFlow. I would like to note that this course focuses on learning how to use TensorFlow and how to create deep learning models. I will not focus much on explaining the different deep learning concepts and the math behind it. Instead, I will give a brief overview of the different layers we're going to be covering in this notebook, and then give you a number of resources that you can use to review those concepts or learn more about them. A convolutional layer is composed of multiple tensor operations. First, you've got the dot product between the weights and the input. Then you add a bias and you pass all of the results into an activation function. And that gives you the output of your convolution. A convolutional layer is usually applied to an image. And an image is a 3D tensor, where the width and the height represent the pixels, and the depth of that tensor are the color channels. And since this is a colored image, we've got 3 color channels. If we set the padding to same, the convolutional operation doesn't affect the size of the space features and only changes the number of feature maps. So in this convolutional operation, we can see that we went from 3 feature maps to 1, 2, 3, 4, 5 feature maps. The convolution is obtained by sliding a window, in this case a 3x3 grid, across the entire image and computing the activations. If you want to learn more about convolutional layers and convolutional neural networks, I highly recommend that you check out those links. This gives great explanations and intuitive overviews on how this works. Now let's briefly go over pooling layers. A pooling operation is simply downsampling the image. You can see here the downsample is done by a factor of 2, going from 224 to 112. The downsampling is only done on the spatial features of the tensor. And we can see here that the feature maps 64 was not changed and remains 64 after the pooling operation. We will use max pooling, which basically means that the downsampling is done by only keeping the feature with the highest activation and discarding the rest. If you want to review pooling concepts more in depth, I recommend to check out this link. Now let's go straight to the code. Building models with TensorFlow can create a lot of boilerplate code that quickly becomes unreadable and unmaintainable beyond a few layers. For example, let's go over combining two convolutional layers with a max pooling layer with native TensorFlow. First, we initialize our graph. Then we need to set up a placeholder for our input. If we set our input as an image, then we've seen that a single image is a 3D tensor or a cube that is 32 by 32 by 3. So if we have multiple images, we have to add another dimension. These dimensions represent the batch size. We set to none because we want that batch size to be arbitrary. We start a variable scope, which we call tf native conv, and we start another scope for our first convolutional layer. So as input to a convolutional layer, you need two inputs. You need the weights and the biases. The weights, as we've seen before, is a 4D tensor that has a 3x3 kernel, and that maps from our input 3D image to 64 feature maps. We set up an initializer, and we set it to a trainable variable. Then we combine the inputs with the weights to the convolutional operation and give it a stride of just 1 in both dimensions, and ask the convolution to have a padding of same, which means that the spatial features of the input will be the same size as the output, and only the feature number is going to change. Then we initialize our bias, and we add it to the output of our convolution. Finally, we pass the output through an activation function. In our case, we've chosen the RealLoo activation function. For the second convolutional layer, it's exactly the same. We set up a variable scope and repeat the same exact thing, except this time we're going from 64 feature maps to, again, 64 feature maps. So we're not adding any more feature maps. We have a convolutional operation, we initialize our bias, add it, and pass it to our activation function. Finally, we pass the result through our max pooling operation, which has a given kernel size of 2 by 2 and a stride of 2 by 2. Now let's inspect the variables in our graph to make sure we've done it correctly. So we've got our first weight from the first convolutional layer that has a 3 by 3 kernel and maps 3-dimensional feature map to 64. And then we've got the associated bias that has the same matching output feature size. The second weight looks correct. We're going from 64 to 64 with the appropriate bias vector. Now let's look at the inputs and outputs of our graph. So we started off with an image, which we know is 32 by 32 by 3. And then the output of our graph gives a 16 by 16 and 64. The 64 comes from the convolutional layer, where we went from 3 feature maps to 64 feature maps. The space features were reduced from 32 to 16, and that was done by the max pooling layer that downsampled our image by a factor of 2. Now let's see how we can rewrite this same code more concisely using TensorFlow-Slim. TensorFlow-Slim provides a number of high-level layer abstractions that allow to combine multiple operations into one function. For example, the function slimconv2d combines multiple operations into one. It creates for you a weight and a bias variable. It convolves the weight with the input from the previous layer, adds the bias, and then applies the result to the activation function. These are the arguments for this function. This is for your own reference. Let's go straight to the code and see how we use it. So you can see straight away that the code is much more concise than before. The beginning is the same. We need an input placeholder for our image. You can add the variable scope for the model, but it's not necessary anymore to add a variable scope for every individual layer. since now the scope is included as one of the parameters of the function. The function takes in the input tensor, the output dimension of the convolution, and the feature space size of the kernel, which is simply 3 by 3. We add the padding, the initializer, and that's it. It does the rest. It initializes the weights, the bias for you, and adds the activation. The second layer is exactly the same, since the output feature map is also 64, and the function automatically infers the size of the input feature maps. Then we can simply add the max pooling function. And here it just needs the input, the 2 by 2 filter size, and the scope name. When we inspect the model, we can see that we have exactly the same graph, with the same parameter size, the same input and output shapes, but this time with just a fraction of the code. Now we're going to see how we're going to make this code even more concise using meta operators provided by Slim. TensorFlow-Slim provides two meta operations called Slim repeat and Slim stack. This allows you to repeat the same operations multiple times and reduce your code size even further. So now we're going to look at Slim repeat, which takes an input and then you simply set it to how many times you want to repeat a specific layer and give it the required arguments. So here we can see that our model is even shorter now. Because we had two convolutional layers back to back, we can combine them into one operation using the Slim repeat operation. We give it the inputs and we tell it to repeat twice this Slim conv2 layer. And both of the layers have the same output feature map and the same kernel size, as well as padding and initial weight initialization. And then we pass it through our max pooling operation again, just as before. By inspecting the graph again, we can see that we've got exactly the same thing. But this time, we're able to reduce our model size to basically just 2 lines. Let's look at an example with fully connected layers. A fully connected layer is one of the most basic blocks in neural networks. Again, I'm not going to go in full detailed explanation what is a fully connected layer. So if you want to review that concept, please check out the links below right here. But basically, what is a fully connected layer is simply a dot product between your entire input and your weight matrix. Then you add a bias and you pass through the entire result through an activation function. We're going to see how we can stack those fully connected layers together to create a multi-layer neural network. Although these neural networks can be very simple, in practice, writing in code can be quite lengthy and repetitive. In addition, to make it more interesting, I've also added a dropout layer and a softmax layer. If you want further explanation on what these layers mean, again, I highly recommend that you check out these links. But basically, a dropout layer is used to regularize your model so it has better generalization on unseen data. And the softmax layer takes in the output of your scoring function and squishes the results between 0 and 1 to give you output probabilities. So let's first look at the code with native TensorFlow. So this time, because we're dealing with fully connected layers, the input only needs to be 2-dimensional. One dimension for the batch size and another dimension for the number of features you have. In this case, let's say our input has 512 features. We set up our variable scope, our layer scope, and then we need to initialize first the weight variable, which is a matrix of 512 to 1024. So in that layer, we're doubling the number of features that we have. Then we also need to initialize a vector, and that vector shape needs to match the output of our weights. Then we take the dot product or the matrix multiplication between the input and the weights. We add the bias and then take the output and pass it through our activation function. Then the rest is very much the same. We repeat the same thing for the second layer, but this time going from 1024 to 556, and repeat again the same thing for our third layer, going from 256 to 10. And let's imagine for this example, we need an output size of 10 because we want to classify over 10 classes. We then take the output through the dropout layer with a dropout probability of 0.5, and then pass it through our softmax layer. Let's examine the variables in this graph. We've got our first weights, which take our data from 512 features to 1024. Then we go from 1024 to 256, and finally 256 to 10. And so we can see that our inputs start off the 512 features, and we end up with what we wanted 10 features to classify over our 10 classes. TensorFlow-Slim also provides a nice wrapper function for the fully connected layer. Its implementation is very similar to the convolutional layer we saw earlier. So let's look at the code. We can see that our code is now much more concise. We don't need to initialize the weights, the biases for every single layers, as well as setting up viable scopes for each of those layers. What the function takes in is the input tensor, as well as the output feature size. Then you just have to give it the weight initializer of choice and repeat that for every layer. The only thing that changes here is the output feature size. That goes from 1024, 256, and then 10. And then the rest is the same. You apply the dropout layer and then the softmax layer. And so when you analyze the graph, you can see that we've got exactly the same thing with a much more concise code. In this case, we could not use slim repeat because some of the parameters in the different layers were actually different. But TensorFlow-Slim provides us with another meta operation, which is called slim stack, which allows us to repeat some layers by applying different arguments to each of them. So now we have condensed our model even further by using slim stack. We give it the input, we tell it what is the layer we want to repeat, in this case slim fully connected, and we give it a list of the different parameters for those layers. So the first layer is a 1024 output feature, then 256, and finally 10. We give it the initializer and then we give it a scope. And the rest is the same. We pass it through a dropout and then softmax. And we can see that again, we've created exactly the same model, but effectively by only calling 3 functions. In this lesson, we're going to go over scopes in TensorFlow-Slim. And we're going to see how we can use scopes to build even deeper neural networks easier. Native TensorFlow already provides us with a number of scoping mechanisms that helps us organize and simplify our code. We've seen them already. These are name scope and variable scope. These allow you to isolate the names and the variables within your model in a scope so that they don't interfere with each other as you initialize different layers. On top of that, TensorFlow-Slim provides a new scope called argument scope or arg scope. These scopes allow you to specify default arguments for specific operations within that scope. These operations are usually layers like convolutional layers, fully connected, max pooling. These layers have a number of arguments necessary to define them. This often means that you have to repeat those arguments multiple times as you initialize the different layers, and this becomes increasingly cumbersome as you define very deep neural networks. To give you an idea of how deep those neural networks can get, let's go over a couple of popular architectures that have appeared over the years. So we have the classic AlexNet that came out a couple of years ago. And by today's standards, it's actually a pretty shallow neural net in comparison. But already you can see that it repeats multiple times the same layers throughout its architecture. You've got the convolutional layers, the pooling layers, the fully connected layers. Then you have the very popular VGG neural net, which basically takes the AlexNet to the next level. The architecture itself hasn't really changed, but we can see that now we've repeated the same layers multiple times to make the neural net even deeper. Recently, Google has also introduced other types of architectures, such as the inception net, which takes neural networks to the next level by making them even deeper and by introducing splitting branching and merging branches within the neural net, making the architecture even more intricate and as a result, making defining those models also more complicated. Over the years, these models continuously get improved and modified. We can see that a later version of the inception model is even deeper and more intricate than the original one. And this is not even the latest version of the inception. Today's inception model would not even fit on the page. There exist other types of neural networks that we don't have time to get into. These are called the residual networks, the dense network, and they can be even deeper than one we've seen here. And these models provide state-of-the-art performance for image classification. So if you're interested and curious about learning more about those models, I've provided links for both of them right here. In this notebook, we're going to go over slim argument scoping and also over a couple of other slim functions. So let's go straight into the code. First, we need to import TensorFlow. Then we can import some of the helper functions we've used in the past. So now let's go over the argument scoping function. ArgScope stores the default arguments for the given set of layers or list of operations. It takes in two types of argument. The first is a list of all the operations in your scope. And these are usually convolutional layers, fully connected layers, max pooling. Then you need to provide a list of all the keywords and values that are associated with the parameters for each of those operations. Let's go through an example to get a better idea of how that works. In this example, we're going to see how we can build an 11-layer neural network by using argument scoping and see how that makes our code cleaner, simpler, and easier to maintain. We're also going to see how we define argument values, but also how we override them. And there are two ways to override argument values. The first is locally, by defining the argument directly in the function call. The second is by using nested scope and defining multiple argument scope within each other. Now let's dive into the example. Before we create the model layer by layer, we first need to define the argument scopes of that model. We're going to start by creating an argument scope only for the convolutional layer and the fully connected layer. Then we need to set up the default parameters for those two layers. For example, we want the convolutional layer and the fully connected layer to both have an activation function that is equal to the ReLU. Then we want their weights to be initialized with a truncated normal initializer. We want the biases to be initialized by a constant initializer of 1. And then we want to apply a regularization of L2 on the weights. In this example, I've left out the bias regularizer and left it to none, because in practice, it is less common and even less useful to apply regularization on your biases when your data has been pre-processed appropriately. So for example, in an image, that would mean mean centering. Then we want to apply a second argument scope within that scope, specifically only for the convolutional layer, which have its own parameters that we want to set. So we set the kernel size to be a 3x3 grid, and I want the padding of all the convolutional layers to be the same. Here, we're giving an example of how we can override a default parameter by creating nested arguments. So we've already defined the bias regularizer, but we define it again in this scope to a constant initializer of this time 0. That means that the convolutional layer will have biases that are initialized to 0, and the fully connected layers will have biases initialized to 1. In practice, it's actually more common to initialize your biases to 0, because you already randomly initialize your weights, and so that already provides the asymmetry that you need to break during the first iterations of your model. We're going to go even deeper and add another argument scoping for this time the max pooling layer. And we set up the default parameters to a kernel size of 2x2 and a padding of same. Okay, so we spent a lot of time creating all those argument scoping for those different layers. And now we can finally build and design our model. And we can see that it makes the model building very intuitive and very concise, allowing us to write much cleaner code. We now can omit all the argument values that are common to all the different layers and only concentrate on the arguments that differ from layer to layer. We're going to use the slim repeat function that we have seen in the past to apply two convolutional layers back to back. Both of those convolutional layers will have a feature map dimension of 64. We then apply a max pooling layer that downsamples our data. We can then apply the convolutional layer a second time. Similar as above, we apply two convolutional layers, but this time the feature map dimension increases to 128. We then apply a downsampling layer, which is max pooling 2D. And now let's say that we're done with applying convolutional layers to our model and we want to go into fully connected layers. We need to transform our data from 4D tensors to 2D matrices. And to do that, you can use the slim flatten function. You can now feed in your data into a fully connected layer. The first layer, let's say we want the output dimension to be 1024. We then apply a dropout layer, which applies regularization to our weight by constraining the learning of our model. And we can set the dropout probability to be 0.5. We can repeat that process for a second fully connected layer, and this time we want the output dimension to be 256, followed again by a dropout layer. Let's say we want our model to make a prediction over 10 classes. We therefore need our model to end with a dimension of 10. So we define a final fully connected layer, this time with an output dimension of 10. Here's an example how you can override the default argument within the function call. So as we've seen before, all the previous layers had activations of ReLU. But now we want the final layer to have an activation that is none, therefore no activation. We call it the linear layer, because we want the output of our model to give us scores across the different classes that we can feed into a softmax layer. So we then can feed this data into the softmax layer. A softmax gives us class probabilities across all our classes. What it does, it squishes all our scores between 0 and 1 and normalizes them so that they add up to 1. So we actually get at the end a categorical probability distribution over our output vector. This allows us to do two things. It allows us to make predictions. The network will tell us which class it thinks is the most likely, and it will allow us to compute the loss. By comparing those probabilities with the true labels, we can compute, for example, the cross entropy loss, and then backpropagate our errors throughout our model using backpropagation and update our model weights using batch gradient descent. Let's now examine the model weights that were automatically generated by the Slim API and see if they make sense. To generate the TensorFlow graph, we first need to initialize the graph and then create a placeholder for our 4D input image that is a 32 by 32 by 3 image. And then we can simply call our Slim model function by giving it the inputs and getting out the outputs. We can now inspect the variables by doing Slim get variables within the scope given. We can see that our first convolutional layer has a 3 by 3 kernel and transform our data from 3 to 64 feature map, which makes sense because we started off with 3 channels in our image. We have biases that match the output feature map of our layer. We then go through a second convolutional layer, again with a 3 by 3 kernel, going from 64 to 64. If you remember correctly, we had 2 layers that both output 64 feature maps. We then go through the second convolutional layer, and we increase the feature maps from 64 to 128. And same thing for the second layer, we go from 128 to 128. Then we move on to the weights for the fully connected layers. And we can see that we had to move from a 4D tensor to a 2D matrix with an output dimension of 1025. Then we have the second layer with an output dimension of 256, and the final layer with an output dimension of 10. So the model was initialized correctly, and all the weights make sense. We can also look at the input outputs. We start off with an image that is 32 by 32 by 3, and we ended up with the softmax that has an output dimension of 10. But what if we want to see how our data is transformed and changes shape as it goes through the model? TensorFlow-Slim allows us to do that by providing us with a set of helper functions that allow us to peek into the layer structure of our model. As neural networks get deeper and more complicated, it's important to keep track of the shape of the data as it passes through every layer operations in the graph. We can inspect those layers by using argument scoping and another Slim function called convert collection to dictionary. Let's look at an example and see how it works. So you initialize and construct your graph just as before by creating a placeholder for your input and calling your Slim model function with the inputs and getting the outputs. The only thing that changed is that now you add another argument scope that is able to collect all the outputs of your layers. In this case, we only look at the layers convolution, fully connected, and max pooling. We're not interested in layers such as softmax or dropout because those layers don't actually change the dimension of our data and are therefore not very interesting. We can then collect our endpoints using the convert collection to dictionary. We can now inspect both the weight of our model and the layer transformations within our graph. We can see that after our first convolutional layer, our image has been transformed from having 3 feature maps to 64 feature maps, while remaining a spatial dimension of 32 by 32. The second convolutional layer doesn't change the dimension of the input data, but then passing it through the max pooling, the data gets downsampled by a factor of 2 and is transformed to an image of 16 by 16. It's important to note that a max pooling layer doesn't actually affect the number of feature maps. and only the spatial features. We then pass it through the second convolutional layer that increases the feature maps from 64 to 128, and passes through a second convolutional layer that doesn't change the shape. We then have the final pooling layer that downsample our data once again to an 8x8 image. We then make the transition from 4D tensors to 2D matrices as they go through the fully connected layer. We now have an image that is represented by a vector that has 1024 features. We then further compress our representation until we get to a feature size of 10 that represents our 10 classes. In part 2 of this lesson, we're going to go over batch normalization and how we can incorporate it in our model by using argument scoping. In part 2 of this lesson, we're going to go over batch normalization and how we can incorporate it into our model using argument scoping. Batch normalization was created as a response to the need of building deeper neural networks. As people started to create deeper and deeper neural networks, they've noticed that a number of problems arise, making training more difficult, unstable, and at times even hurting performance. There are a number of problems with training very deep neural networks. Two of the main ones are internal covariate shift and vanishing gradients. Internal covariate shift is basically the concept of having internal input distribution in the layers of your network to change over time. Especially when those shifts happen in the first few layers, those change in distributions get amplified down the network and destabilize the training, making it slower and less performant. Vanishing gradients often happen when you use activation functions such as the tanh and the sigmoid function. These activation functions tend to get stuck in the saturation region during training. Those regions of those activation functions are constant, and therefore their gradient is 0. Since training is done by computing the gradients, if the gradient is 0, the training stops from that point on. A way to alleviate that effect is to use instead ReLU activation functions that do not have a saturation region for positive values. Nonetheless, you still need to use smaller learning rates and careful initialization when you're training very deep neural networks. So what is batch normalization? Batch normalization is this widely popular method that addresses various issues related to training deep neural networks. It has led to significant performance improvements in state-of-the-art models by making normalization part of the neural network architecture itself. In the same way, we spend careful time pre-processing and normalizing our input data as we feed it into the neural net. What if we apply a similar normalization scheme at every single layer in our neural network? And that's exactly what batch normalization does. Concretely, that means that we have to compute the mini-batch statistics of our data between every single layer. That includes computing the mini-batch mean and the mini-batch variance. With these values, we're able to normalize our data with those approximated means and variance. And then using gamma and beta, we can transform our data by scaling it and shifting it by a certain amount. These parameters are trainable and are therefore learned during training of the model. Here we have a graph that compares the performance of adding batch normalization to the inception model. On the y-axis, we've got the validation accuracy of the exception model for a classification task. And on the x-axis, we've got the number of training steps it takes to achieve that accuracy. The black line represents the inception model without batch normalization, and all the other lines include batch normalization in their training. We can see that they're able to achieve similar validation accuracy much faster. By keeping in check the internal distribution of the data between every layer, you're now allowed to increase the learning rate to much higher level without disturbing or destabilizing the training process. In this graph, the learning rate was increased up to 30 times the original learning rate. And we can see that they were able to achieve very similar validation accuracies in about a tenth of the original number of training steps. The advantages of batch normalization are that you can get faster convergence with higher learning rates, and you therefore benefit from the more stable input distribution that reduces the covariate shift in your model. And since training is more stable, your gradients are less sensitive to your input data or your initialization. An added bonus that you get with batch normalization is some level of regularization that prevents overfitting and even reduces the need for using dropout or L2 or L1 regularization. Moreover, you can even now train your networks with saturating non-realities such as sigmoid and still can manage the vanishing gradient problem. We can see here in the graph for the pink data, they use the sigmoid function and still were able to learn and train the data pretty well. In this other example, we're looking at the test accuracy of the NMIS dataset with and without batch normalization. We can see that batch normalization allows you to both achieve higher accuracy and also faster training time, to the point that it almost seems like the line jumped straight to 95%. We also get to see how the distribution of the internal data changes over time. And we can see that without batch normalization, that distribution tends to be unstable, and this instability makes training harder and slower. Whereas with batch normalization, the transition is much smoother, allowing it to train at a much faster rate. If you're interested in learning more about batch normalization, I highly recommend that you check out the original paper right here. I've also provided a couple of other links that go in more depth explaining how batch normalization works. Let's go through an example and see how we can include batch normalization into our model. Adding batch normalization to our model with TensorFlow-Slim is actually very straightforward. Here we have exactly the same model we've had before, but we've only changed one line. And we just need to add this line to add batch normalization to our model. So what that means is that within the argument scoping of the convolutional layer, we want every convolutional layer to apply a batch normalization. TensorFlow-Slim will automatically generate and initialize all the necessary weights associated with this layer. So now let's inspect the variables of our model and see what changed. We build our graph just as we've done before, and then we call the inspect variable function and the inspect layer function. And this is what we see. The batch normalization parameters have been automatically added to every single convolutional layer. In this case, 4. We have our normal weights for our convolutional layer, and then we've got our 3 parameters for our batch normalization: beta, moving mean, and moving variance. TensorFlow-Slim is smart enough to notice the batch normalization and remove the biases from every layer by replacing them with those parameters. And that's it. You've implemented batch normalization into your model. In this lesson, we're going to go over a multi-layer feedforward neural network in TensorFlow-Slim. This lesson is divided into 4 parts. First, we're going to generate a 2D dataset for a 3-class classification problem. We're going to build a simple 3-layer feedforward neural network using TensorFlow-Slim, and then train and evaluate the neural network on a training set and a test set. Finally, we will visualize the learned decision boundary of the neural net and see how it performs on unseen data points. Let's import TensorFlow and as well matplotlib, since we'll be plotting our data set. Let's import some helper function. I have provided you with a class called spiral dataset, which will allow you to generate your own spiral dataset by calling the generate spiral dataset function. This will create a 2D dataset with 3 classes, and you can set the number of points you can have per class. So for the training set, we're going to set 200 points per class, and for the test set, we're going to set 100 points per class. You can as well add noise to your data to make your dataset more realistic. We now have a training set that has a 2D feature space and 600 points, as well as its associated target values. If you are curious to learn how the spiral dataset and plot was created, you can check out the Python file provided called Data Generator. Under the spiral dataset class, you will see how the data is generated with the generated spiral dataset function and how it is then plotted using the plot spiral function. So this is the dataset we've just generated. We can see that we have 3 distinct classes. We've got a red class, a green class, and a purple class. The black dots are unlabeled data coming from the test set. We can see that there is a clear pattern for every class, but also that there's some added variance to the dataset due to the noise that we've added when we generate the data. The added variance makes the data more realistic, but also makes it harder for the neural network to learn the underlying signal. We want our model to concentrate on the signal and learn those patterns while at the same time disregarding the injected noise in the dataset. In other words, we want the data to learn a generalized representation of the data, allowing to perform well on seen and unseen data. Just as an example, let's regenerate the data, this time with less noise, in order to see what is the underlying signal of the data. So let's set the noise to 0.1 for the training set and 0.1 for the test set. Now the underlying signal is much clearer, and therefore the task of coming up with the decision boundary that will separate those three classes becomes a much easier problem. Each class is nicely packed together with barely any overlap, as opposed to what we had before. For example, let's go back to 0.5. We can see now that coming up with the decision boundary becomes a bit more ambiguous, especially when it comes to classifying black points that are between two classes. Deciding to which classes those black dots belong to becomes difficult, and the neural net will have to learn to deal with that uncertainty. This is the code for the 3-layer feedforward neural network that we will train on our generated spiral dataset. This neural network is very simple and can be written very concisely thanks to TensorFlow-Slim. The model is only 3-layer because, as we'll see, it doesn't take much for the neural network to learn the underlying pattern and classify the data correctly. I have defined this model for you in the Slim models file that you can now import as DBClassifier. DBClassifier is a class that defines the exact model we've seen earlier with some added functionality. The DBClassifier inherits from the model class, which gives us other functionalities such as examining the model structure, which we've seen before is very handy. The model is only made of fully connected layers. We start by defining an argument scope that defines parameters for the fully connected layer only. We set the activation to be real loop, and we want the weights to be regularized with an L2 regularizer. The first layer increases the dimensionality of our input to 64, and then our second layer reduces the dimensionality to 32, and finally our final layer output dimensionality of 3, because we're going to be predicting over 3 classes. It's important to note that the last layer is a linear layer with no activations. And to do that, we need to override the argument scope by setting the activation function to none. Let's now define our model and examine its structure. By calling the DBClassifier class, we simply have to add the input dimension and the output dimension to define our DBClassifier model. In our case, we've got a 2D dataset, so we've got an input dimension of 2. And since we're classifying over 3 classes, we've got an output dimension of 3. So we can see that we indeed have 3 layers. Our first fully connected layer increases our dimensionality to 64, and then our second layer to 32, and finally our prediction layer to 3. We've got 3 sets of weights, which transforms our data. The weights for the fully connected layer transform our data from a 2D to 64 nodes. The second layer goes from 64 nodes to 32. And finally, the prediction layers goes from 32 to 3. We have now checked that our model is defined correctly, and we can now move into the training phase. To train our model, we're going to use the provided class Model Trainer Evaluator. In this lesson, I will not go in detail about how this class works, because it will be covered in depth in a later session, which will be about building training routines in TensorFlow-Slim for neural networks. All we need to know for now is that the Model Trainer Evaluator takes a model parameter that we've defined earlier, DBClassifier model, a dataset. We can then name the dataset. In this case, we're going to name it Spiral, and then we can set a checkpoint directory where the parameters of the models will be saved once the model has been trained. Our model can now be trained by calling the train method. It takes as input the dataset that we want. So in this case, we'll be training on the training dataset. And then we can set the parameters of the model, the weight decay, which represents the regularization term, the learning rate, which is 0.05, and then we'll be training over 1000 iterations, and log the cross-entropy loss every 100 steps. For this example, the training has already been done for you. Since this is a relatively small data set and a small neural network, the training happens quite rapidly. We can go through about 200 global steps per second. We can also monitor the learning of the model by looking how the loss decreases over the different time steps. Now that our model has been trained over our dataset, we can now evaluate its performance by calling the evaluate function. We're going to compute our metrics by only running the evaluation once over the dataset, and we're going to compute it using our training dataset for now. In this lesson, I will not go in details about the implementation of the evaluate function, because this will be covered in depth in a later session that will be about building evaluation routines in TensorFlow-Slim. For now, we can see that our model performs really well on our training set, reaching accuracies of 94% and recall of 98%. Let's now define a function that will allow us to compute the accuracy of our model, both on our training and test set. To do that, we need a function that is able to reload the model parameters that were saved earlier to disk and perform inference on the model to make predictions. Performing inference on a neural network is when the model is only run forwards. There is no backpropagation, nor any parameter updating. We start by initializing our graph and then initialize a dataset provider. This dataset provider provides us with a function called load batch spiral that will transform our NumPy data into TensorFlow tensors objects. If you want to see the implementation of that function, you can check out the slim data provider file. It is a simple function that takes a dataset of NumPy arrays and transforms it into TensorFlow constant tensors. One tensor for the inputs and one tensor for the labels. We can run inference on our model by passing in the inputs into our graphs and getting out the class probabilities. To transform those class probabilities into predictions, we simply pass them through an argmax function that will predict a class for each observation. We can now compute the accuracy by using the slim metrics accuracy function that compares all the predictions with all the target values. We now have created a graph that computes the accuracy of our model. All we need to do now is restore the old parameters from the checkpoints with this function and run a session on the prediction and accuracy nodes. So we get an accuracy for the training set of 94%, as we've seen before, and for the test set, we get an accuracy of about 92.6%. I leave it to you to play around with the model parameters, such as the learning rate, the regularization coefficient, and the number of iterations, and try to improve on this score without overfitting to the training set. The spiral dataset also implements a plotting function that plots the decision boundary learned by the model. If you're interested to learn how this plotting function was implemented, you can check the data generator file, and on the plot classifier, you will see the code that generates this decision boundary for the learned model. We can see that the model did a very good job at coming up with a decent decision boundary for this dataset. It was able to learn the underlying pattern behind the dataset. And thanks to some regularization, the decision boundary is relatively smooth and is not too much affected by the noise in the dataset. Finally, let's overlay the test set data onto the learned decision boundary and see if that boundary still makes sense on unseen data. And indeed, it seems like the model was able to generalize pretty well and create a decision boundary that is able to classify correctly to some extent data that it has never seen before. The decision boundary could be possibly improved further with a bit more fine-tuning, but in general, the test set results here are satisfactory, and we can assume the model has learned a useful representation of the data. In this lesson, we're going to build a deep convolutional neural network with TensorFlow-Slim so that we can train it on an image classification task using our flower dataset. This is the code for our CNN model. In this model, we're going to be using everything we've learned so far. First, we define a slim argument scope over both the convolutional layer and the fully connected layer. For those two layers, we're going to apply an activation function, that is the ReLU one. We're going to apply weight regularization with slim L2 regularizer, and we're going to initialize the weights and the biases. The weights are going to be initialized with the truncated normal, and the biases are going to be initialized with the zeros. We can also set default parameters for the convolutional layer. We want all our convolutional layers to have a kernel size of 3 by 3 and padding same. We can also set default parameters for our max pooling layers. We want them to have a kernel size of 2 by 2 and a padding of same. Our model is going to be divided into 3 blocks. The first block will be a convolutional layer with an output dimension of 64. In this case, we're only repeating that convolutional layer once. We then follow this first block by a max pooling layer, which downsamples our image size by 2. The second block is very similar as the first one, except now that the convolutional layer output dimension is 128. And we now repeat twice that convolutional layer. We then follow it another time by a max pooling layer that downsamples our images a second time. Finally, we have our third pooling layer, and this time we're repeating the convolutional 3 times with an output dimension of 256. We finally pass it through a third time through a max pooling layer, which now gives us an image of 8 by 8 pixels. The end of our model is made of 3 fully connected layers. In the past, we've used the slim fully connected function. When you set the kernel size to be the size of the image, the computation turns out to be equivalent to a fully connected layer. The advantage of using a convolutional layer to compute a fully connected layer is that you don't need to reshape the data, and the convolutional function is often better optimized on GPU. Therefore, you end up having better performance by turning all your fully connected layers into equivalent convolutional layers. So here we set our filter size to be 8 by 8, which overrides our previous argument scope. We set a padding to valid, and we want our output dimension to be 1024. For the fully connected layers, we now apply another type of regularization, which is dropout. Then we can apply our second fully connected layer. This time we transform our data from being 40 tensor into a vector, and therefore we can use a kernel size of 1 by 1. Finally, for the final layer, we want the final layer to be a linear layer. Therefore, we set the activation to be none and the normalizer to be none. And that's it. That's the entirety of our CNN model. We're now going to examine the structure of our model and check if it was defined correctly. We can get a definition of our model that we've discussed above by importing the CNN classifier class. This class is provided in the Slim models file. This is exactly the same model definition that we've talked about earlier with some added functionalities. For example, having the built-in function called examine model structure, which we've seen before. I won't go into too much details for the layers because we've gone through similar examples in the past before. So let's go through it quickly so we make sure we have in fact defined our model correctly. As expected, we only define one convolutional layer for our first block, which is right here. Then for our second block, we define 2 convolutional layers, which are right here. And for our final third block, we define 3 convolutional layers, which are right here. And between each block, we also define a max pooling layer. So that adds up 3 max pooling layers, which are right here. And finally, our model ended up with 2 fully connected layers, which are right here on top. So we can see that our images started off as a 3D tensor. And as they went through the model and reached the fully connected layers, they transform into vectors, which is exactly what we expect. The parameters also seem correct. The weights and biases for the convolutional layers all have a kernel size of 3 by 3. And then when we reach the fully connected layers, we end up with kernel size that are equal to the size of the image at that point. So 8 by 8, and then it goes to 1 by 1 when the image turns into a vector. Now we're going to learn how to pre-process our raw images so that they can be fed into our neural network model. We're going to use the Dataset provider class that is located in the Slim dataset provider file. So right now we're going to go through the main functionalities of the dataset provider class. The main function of this class is called preprocess image, which takes in a raw image and desired output height and output width and transforms the image by cropping it and normalizing it. So if we go through step by step, we can see that we first transform the image into floats right here, and then we can resize and crop the image using the resized image with crop or pad function by providing the raw image and the output height and the output width desired. We finally can normalize the image using the function per-image standardization, which is a linear scale of the image to have a zero mean and unit variance. The second function we're going to look at is called load batch CNN. This function will help us load batches of images that we can feed then into our neural network during training at every iteration. The output of this function are two tensors. One tensor for a batch of images, which is a 4D tensor, and then another tensor which is a batch of labels, whose value range between 0 and the number of classes. We then initialize a dataset data provider by setting the common queue capacity to 32 and the common queue minimum to 8. We then extract the images and the labels from the data provider by calling the get function. We now pass the raw image through our preprocess image functions that we talked earlier and resize and preprocess our images. Finally, we can set a train batch object will allow us to retrieve batches of images as we iterate through our training. We first set our batch size, and then we're going to set the number of threads to be 1, since we only want one queue. And we're going to set the capacity to be twice the size of our batch. So here we are. We've managed to build a deep convolutional neural network for an image classification task, and we've also learned how to pre-process our data so it can be fed into this model. In this lesson, we're going to download and explore the DBpedia dataset. It is a very popular dataset used for text classification. The DBpedia dataset is an ontology that is constructed of about 14 non-overlapping classes. Each sample consists of a short text that is about 100 words. Each of those samples can be categorized in one of those 14 classes. In this version of the dataset, each class contains 40,000 training samples and 5,000 testing samples. That adds up to a total size for the dataset of 560,000 for the training set and 70,000 for the testing set. So the 14 target classes are the following. You've got text that talk about animals, plants, films, album, companies, artists, athletes. So you can see that those classes are definitely not overlapping, and the goal of the task is to pass those strings of text through a neural network and have it predict the correct category. I've provided for you dataset helper function that would allow you to download and load the DBpedia dataset for you. So you can look at it right here. This file, what it does is it basically downloads the dataset for you and then decompresses it into different files. You have one file for the training set, one file for the test set. You can also pass in a number of parameters, such as the size in which you want the data to be. Since this is just for exploration purposes, we're going to ask for the small data set, which shrinks our data set by a factor of 1,000. So by passing the small parameter, we're basically only loading 0.1% of the total data set. So that amounts to just 560 training samples and 70 test samples. The first time you call that function, it will actually download the data in your local directory. And then every time you call that function again, it will simply load it directly from disk. I've also included here two other helper functions, and this time those are for exploring the dataset. So this first one loads the classes file and loads them into a list. The second function loads in the data and then picks a random sample from the data and returns the actual text, the title, and its target class. So now we can load the class file with the load target class function. And we can see that as expected, we do have 14 classes in this file. And these are obviously the same names we saw earlier. The order in which those classes are do matter. because the index of the name within this list represents the ID that is used in the other files, such as the training and test file. So now we can explore the data by calling the function explore DBpedia data. We pass in the data, the classes, and then tell it how big of a samples we want. So in this case, we'll just look at 5 samples. These samples are generated randomly every time you run that function. You will probably see different examples if you run it yourself. So the first one is an office holder. So that's a text that describes some kind of politician. The second one is written work. So in this case, this is a text that describes a comic book, which is fantastic for. Then we have a natural place, in this case, a river. And you can see that the size of the text varies significantly from sample to sample. And that could be a problem for some type of neural networks. And so we're going to see in a future lesson how we can apply some tricks to those text sequences to deal with those variable lengths. And then this other one is an artist, so it seems to be a Japanese author. And the last one is a company called NextGen, and it's an Indian publishing company. So now that we have a good understanding of this data set, we can now move on into building the model. In this lesson, we're going to learn how to build a convolutional neural network with TensorFlow-Slim for a text dataset. Convolutional neural networks are typically used in computer vision. CNNs, in fact, have been responsible for major breakthroughs in the last couple of years in image classification. However, CNNs can be used to solve other problems, such as natural language processing, which involves tasks with text data. Text data, as opposed to static images, is sequential in nature and therefore have temporal dependencies, as opposed to images that have spatial dependencies. For that reason, recurrent neural networks are particularly naturally suited to deal with text data. RNNs have connections between their units that form a directed cycle, as you can see right here. This creates an internal state of the neural network, which allows it to exhibit dynamic temporal behavior. And so in this example, you can see that as you feed in input data, first the neural net updates its internal states and then outputs a value. And if you unroll that neural network, you get something that looks like this. So unlike a feedforward neural network, an RNet can use its internal memory to process arbitrary sequence inputs. The problem with RNNs is that they tend to be computationally heavy compared to CNNs, and therefore it makes them slow to train, especially on high dimensional data like text. Moreover, they tend to be hard to train because the learning can suffer from a problem such as vanishing and exploding gradients. On the other hand, CNN tends to be really fast and highly optimized on GPU. The problems with CNNs is that they need data that basically looks like an image vector representation. So in this notebook, we're going to see how we can apply some tricks to our text data in order to redefine it in the context of an image so it can be fed into a CNN. The way we represent an image in vector representation is by treating every pixel as a different feature or dimension in the data. So for example, if we have an image that is 4 by 4 pixels, then that means that our input data has 16 dimensions. Each pixel is represented as a floating point number, which we usually normalize to be centered around 0. That allows us to create a 3D tensor of the image where the first dimension represents the vertical number of pixels, the second dimension represents the horizontal number of pixels, and the final dimension is the number of channels. So for colored image, that's 3, and for black and white images, that's just 1. So how can we represent text in the same way using a vector representation? The first step is to tokenize your text, either at the word level or the character level. Then we need to represent our tokens as vector embeddings of floating points. That means that each vector is represented by a vector of floating point numbers. Another way of doing that is to use one-hot encoding. One-hot encoding is when the vector is 0 everywhere except 1 for one dimension. That creates non-overlapping vectors, usually used for categorical variables. And so that allows us to create, with text, a 3D tensor similar to images. But in this case, the first dimension represents the text sequence length, and that's the length of the sequence of our sample. The second dimension represents the size of the embedding of every word or character. And then the last dimension is usually left to 1, as we're assuming that those are basically like black and white images. There's also a difference here compared to images. Images are using 2D convolution when they're fed into a CNN. That means is that the filter or the feature maps are sliding both horizontally and vertically over the image. And so they're using both those dimensions to move the convolution. In a text CNN, the convolution is actually called 1D. It's a 1D convolution, where the feature maps, the filters, only slide vertically along the sequence dimension. The filters always have an horizontal dimension that is equal to the token embedding size, and therefore they can only slide down the vertical dimension as if we're reading through every word. So this is the text CNN models we'll be building in this lesson. And so this is a simplified diagram of what we'll be building. The way this CNN differs from the previous ones we've been building is that first, it uses a 1D convolution instead of 2D. And also, this CNN branches out into 3 branches, and then we combine them together afterwards. And so here are the 3 branches. We have one branch here, another one here, another one here, and then we can see that we apply convolution and then we recombine them together. So let's look at the input. So the input is, how we've seen earlier, we've got a vector representation of our text. So the vertical dimension represents our sequence of words in our sentence or text. And then the horizontal dimension represents the vector embeddings that we've decided to choose. And so in this case, every word has an embedding of 5. We then apply those convolutional layers on those embeddings one by one. The reason we branch out into 3 different branches is because we'll apply different sizes of filters. So here we have a filter of 2, a filter of 3, and a filter of 4. What that does is, if you're familiar with the concept of n-grams, is with a filter size of 2, it's basically you're looking at bigrams and then you're sliding down the window from top to bottom. And that's why you're calling it a 1D convolution, because you only slide down one dimension. And then the second branch is you slide your filter over 3 words, so over trigrams, and the last one is over 4 words. After the convolution has been done, then you applied an activation function over your features. And finally, you apply a max pooling layer that downsamples your data. And then you can finally concatenate all your activations into this vector representation. You can then apply a fully connected layer at the end with regularization and a softmax function to create your classification boundary. And so in this example, we just have 2. Obviously, in ours, we'll have 15. If you want to have more information about behind the intuition and how exactly this model works, I recommend highly that you check out the links I've provided here that explains this convolutional neural networks for natural language processing. And it talks also about representation and how to visualize those word representations. So this is the actual code of the model I've just talked about. And so this implements the model in TensorFlow-Slim. First, we need to set the embedding size. So for our model, we're going to set the embedding size to be 20, and then we want our sequence length to be 100. So that means that every text sample will be truncated to have a length of 100. And then here we set the number of filters to be 10. So initially, our vector representation of text has a filter of a number of channels of 1, and so we want to increase that to 10. So we start by setting an argument scope for both the convolutional layers and the max pooling layers. And then we're going to start looping over this block of code to create our 3 different branches. And so in our model, our 3 branches will have filter size of 3, 4, and 5. We first create the 1D convolution. So TensorFlow doesn't have yet a 1D convolutional layer, but that's not a problem. We can recreate a 1D convolution with a 2D convolutional layer by setting the second dimension of the filter to be the size of the embeddings. And so since the representation has the same size, then the vector has the only choice of sliding downwards to one dimension, and that's create a 1D convolution. The only thing that we change here is the size of the filter, which we've talked about is equivalent to looking at n-grams as we slide down the window. And then we set the stride to 1 in both dimensions. And it's important to get the padding to be valid, because we've been dealing with different filter sizes. It needs to adjust the dimension of the filter appropriately. We then pass the data into a max pooling layer. In this case, it's a 1D max pooling layer that downsamples our data. And then we just append the network into the branch list. Once we've looped through this block of code 3 times and created our 3 branches, we can then concatenate our 3 branches into one vector. And so we went from a tensor to a vector, and so now we can apply fully connected layers. We first apply a dropout layer, which is used for regularization and prevent overfitting. And then we can apply the fully connected layer at the end to create the classification of our data. Obviously, because this is the last layer, we don't need an activation function. And you can notice that I'm using the convolutional layer implementation, but as I've talked earlier, this is equivalent to a fully connected layer if you set the filter size to be appropriate. And so that is a more efficient way of implementing your fully connected layer. So I've defined for you this exact model in the CNN classifier class that you can just import. And so by passing the argument DBpedia, it will automatically retrieve that dataset, that text CNN, because it knows that this is the text dataset. You can set up the number of classes with 15, and then we set the input tensor size to be 100 times 20 times 1. We can now examine the model structure and see if our model was defined correctly. So by first looking at the layers, we can see that we do have 3 1D convolutional layers, 1, 2, 3, and then 3 pooling layers. Those layers all go from filter size that goes from 1 to 10, as we've specified. And then this dimension varies for different convolution because these convolutions do have different filter sizes. And so by setting up the padding to be valid, that's what happens. And then finally, we end up with a vector. So we went from tensors to vector, and we're predicting over 15 classes. And that's what we're getting here for the prediction layer. In terms of parameters, we also have, as we expected, 3 weights parameters for the convolution and then 3 bias parameters. Those are the feature maps we've been talking about. And so since we had 3 branches, we had feature maps of different sizes. We can find them here. We have a feature map of size 3, 4, and 5. And then the rest is the same. They all had the second dimension equal to the embedding size. And they're mapping from a filter number from 1 to 10. Looking at the prediction layer, we can see that here we have a 30. So we have 30 in dimension because we recombine all the branches together that all have a dimension of 10. And so by concatenating 3 branches of 10, we get a vector that has a dimension of 30. And then we can apply the fully connected layer. And so we're connecting it to a vector size that is 15 because we're predicting over 15 classes. So as we have seen, we can't just feed in text data into our neural network. There are a number of pre-processing steps that need to happen before we can do that. And so we'll go over those now. First, we need to tokenize the text into words. And then it is often a good idea to remove the very low frequency words. The reason is text data follows a power law. By removing the low frequency word, we can actually significantly reduce the dimensionality of our data, which will make it easier for the neural network to train on. We then need to transform our training and test data into a sequence of token IDs. They're basically replacing the words with token IDs. Another problem is that CNNs cannot deal with variable input length. And so we need to truncate all of our sequences to a fixed set of length. And so if the sample sequence is too long, we just truncate the extra words. But if the sequence is too short, then we need to add padding. And so that means adding zeros either at the beginning or at the end of the sequence. We then need to generate trainable and regularized vector embeddings for each of those tokens in the vocabulary. We also finally need to create some kind of embedding lookup matrix where we can load all our sequences in batches. This first function is to pre-process the vocabulary data. One of the parameters is minimum frequency, and it will therefore drop any word that has a frequency of 2 or less. We then can pre-process, fit, and transform both our training and test sets, and then calculate the number of words in our vocabulary. We can load the data and pass it through our pre-processed vocabulary word, and then create a nice dictionary with all our training and test set data. Finally, this function creates the vector embeddings for each of our tokens. By passing it the data and the size of our vocabulary, we can set it to 20. This is the size of the embedding size that we want to create. And so this function, embed sequence, will create embeddings that are initialized by a truncated normal and regularized by L2 norm. We set those vectors to be trainable because we want the backpropagation to go all the way down to those word vectors. Now we need to create an embedding lookup where we can retrieve those word embeddings. So by using the TFNN embedding lookup, we can give it the word vectors and then give it the indices of the batch we want to retrieve. And that will give us the input that we can use and feed into our CNN. So we can see that by loading and transforming our data, we now have a vocabulary that is about 1400. That's the number of unique words in our vocabulary. And now looking at the text representation of the data with token IDs, let's take, for example, the training set, and let's take a sample. In this example, we took sample 10. And so sample 10 now used to be a sequence of words, and now it's a sequence of token IDs. Each ID obviously represents a different word. And we can see because this sequence in particular was less than 100, then we had to add zeros. And those are the zero paddings we've been talking about. Finally, we can get a batch by calling the getBatch input. And so we can see that at every time we retrieve a batch, the shape is exactly what we're hoping for. We're getting now a 3D tensor for our input data. The first dimension represents the batch number. So in this case, we have a batch size of 32. And then the second dimension represents the length of the sequence. And so we set the sequence length to be 100. And finally, the last dimension represents the embedding size, which is 20 in our case. Now you know how to pre-process text data into a text representation and then build a convolutional neural network that's able to take in text data and classify them into different categories. Thank you for following this course. This introduction to TensorFlow-Slim comes to an end. Let's wrap up and summarize what we've learned in this course. In this course, we learn how to build readable and maintainable deep learning models, as well as defining complex models much more compactly by eliminating the boilerplate code. We looked at variables, how to create and define different types of variables. We looked at layers and how to create abstract complex layers in a repeatable way. And then we looked at scopes and how we can use them to organize our code and manage default parameters for multiple layers at a time. Then we looked at how to design and build our own neural networks. We first looked at feedforward neural networks trained on our own generated data. Then we looked at convolutional neural network trained on different types of flower images. And finally, we built the convolutional neural network for text classification. If you enjoyed this course and would like to learn more advanced features with TensorFlow, I highly recommend that you check out this second course in a series of TensorFlow-Slim offered by O'Reilly called TensorFlow-Slim for training, evaluating, and tuning deep neural network models. In this second course, you will learn more advanced features in the TensorFlow-Slim API. You will learn to construct and customize your very own loss functions for specific tasks at hand. You will learn about loss functions for regression and loss functions for classification. You will cover binary classification, multi-class classification, and even multi-label classification. You will also cover how to combine those different loss functions together. You will also learn about various evaluation metrics and how to combine them together to measure your model performance in an optimal way. Then you will learn to automate completely the training of your neural net by creating a training routine, as well as an evaluation routine that is both robust and repeatable. Then you will learn to improve your model performance by using fine-tuning on pre-trained models. Finally, you will learn how to use transfer learning to extract layers from previously trained models and bootstrap the training for new predictive tasks. If you're interested in learning about all those new features, then I hope to see you in the next class.